Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 6 of a 7-part mini-series within that playlist dealing with balanced two-factor factorial designs without interactions. And the topic is contrast. Now, as a reminder, our model can be thought of as mu times the one vector. So this is matrix notation, x alpha times the parameters alpha plus x beta plus beta plus epsilon. So the epsilons are normally distributed. And so this deals with factor A, and this is factor B. And so the interests are in both treatment contrasts for factors A and B. So a contrast for factor A is a linear combination of the alphas, where the sum of the constants here sum to 0. And a constant for factor B is a linear combination of the beta components, where the coefficients kj sum to 0. Now, the two contrasts, alpha 1 and alpha 2, or gamma of alpha 1 and gamma of alpha 2, are orthogonal contrasts. So first, if they're contrasts, they're linear combinations of the alpha parameters, but the sum of their products is 0, and that means they're orthogonal. And so similar for orthogonal contrast for factor B, so gamma of beta 1 and gamma of beta 2 are orthogonal contrast. First they're contrasts, and then the product, or it's the vector product or the product of their coefficients, the sum of the product of the coefficients is 0. Now in theorem 1, we're dealing with estimable functions, and we're going to develop linear contrast for this. This is a general setting. We're taking a linear combination of the beta parameters, so beta star. It's estimable if the lambda is part of the row space of the design matrix. And so I have a 4-part mini-series on estimability in this big playlist, General Linear Models Design of Experiments, that goes into great detail about estimability of this linear combination. So then this estimable function is a treatment contrast in the alpha i's. So it's a treatment contrast for factor A if and only if rho m is equal to rho m alpha. Now m is the perpendicular projection matrix on a column space of x star, and then so the full model, and rho alpha is the perpendicular projection matrix on the column space of x alpha. Now the proof is this. So since it's estimable, lambda is equal to rho x star for some rho, meaning it's part of the row space. But if we expand our design matrix into 1, x alpha, and x beta, then we can take that row into each of those. But since it's a treatment contrast, this is 0, and it's 0 for when we pick up the the beta parameters. So there's a vector here, call it C, C1, C2 through CA, which makes this a contrast for factor A. So that is, but notice that rho is orthogonal to this column space, 1 and x beta, right? This is 0, and that's 0. But the column space of 1 x beta, 1 is part of this column space, so it's really just column space of x beta. But that's equal to the column space of the perpendicular projection matrix onto it. But if we add 0 to this, right, we add and subtract j, and we add and subtract m alpha, these column spaces are the same. But this is how we defined m, the perpendicular projection matrix on the whole column space. And of course, this is a perpendicular projection matrix onto alpha, but in a way that it's orthogonal to the one vector. So thus, rho, times this has to be 0, right? But now if you take rho into each of those and then add that to the other side, we get this. But rho times j is 0, so it does, rho transpose m has to equal rho transpose m alpha, okay? So what's intriguing about that, and that it lives in this column space. Okay, so a corollary to this, so let's assume the theorem 1 is true, then M rho lives in this column space. Okay, that's going to be significant in a second. So first, let's take the perpendicular projection matrix onto the column space, pre-multiply M rho, right? So we know that it's going to take this and shove it down into this column space. So let's multiply that out. Oh, and we just said that this is M alpha rho, right? We proved that in theorem 1. So then this times this, since that's idempotent, that's just M alpha rho back. And then J and rho alpha is J. But this is 0. So we just get this. But that is M rho. But so that means M rho is in this column space, right? It shoves it into the column space, but it equals itself. So this has to live in that column space. Thus, it is in the column space, okay? And that's becoming significant in a second here. So, assuming theorem 1 is true, and we have A minus 1 orthogonal treatment contrast, such that, since they're treatment contrast, they're estimable, that means the lambda in front of, has to be part of the row space. So we'll call lambda I, for each one of those, rho I transpose X star, right? Has to be part of the row space. Then M rho I forms a basis for this column space. So these orthogonal contrasts I'm jumping ahead. So now by corollary 1, each M rho I is part of this column space. Now by assumption of orthogonal contrast, this is 0, rho I M rho J, but M is idempotent, so you can multiply it and then you break it into two pieces, untranspose it, and we get this, right? But this implies that M rho I, that this set of vectors are orthogonal, right? Each one of them is orthogonal to the other. All the other vectors in this column space. But since the dimensions of this column space, M alpha minus J, is A minus 1, that means these vectors form a column space. These vectors here, they form a basis for this column space. Now we're getting into the very interesting stuff. So a corollary to this is, assuming theorem 1 is true, let M rho I be one of these vectors, but it's normalized. And that's for all A minus 1 of those vectors from theorem 2. So let's collect those and put it in a matrix called P star. So this comprises of all the orthonormal basis for this column space. So each one of these is normalized. So it forms what's called an orthonormal basis for this column space. Then by property 5 in a video that I have out called Perpendicular Projection Matrices, P star transpose is the perpendicular projection matrix onto this column space. But perpendicular projection matrices are unique. So thus, P star transpose has to equal this perpendicular projection matrix, which is the perpendicular projection matrix onto this column space. So that tells me that we're going to be able to break up the sum of squares for, say, treatment A. And that's what theorem 3 deals with. So assuming theorem 1 is true, then the sum of squares for treatment A can be broken up into the sum of squares for these orthogonal treatment contrasts. So the proof is this. So here's the sum of squares for treatment A. It's this quadratic form. But remember, this is the perpendicular projection matrix, which is equal to this, which is the, deals with the orthonormal basis for the column space of M alpha minus J. But this can be thought of as two vectors, like this. But the way we define P star as the columns of those orthonormal bases, that is this sum, right? So this squared comes over, and then this is the length of the vector squared, which is this. But this right here is how we define the sum of squares for one of those treatment contrasts. So the sum of squares can be broken up into a sum of those orthogonal treatment contrasts, and the proof is done. Now, in the interest of time, we're not going to do this for factor B, but simply say that the same arguments can be made for factor B. So we can break up the sum of squares for factor B into these orthogonal components and then conduct testing on it. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.